Hello, climate changers. So today's lecture, or this lecture, is on dating and global average temperature. Now, just trust me, these are very important elements of climate change. And so, knowing how we do dating and how we figure out global average temperatures of the past are super important. And you'll see here in the background a picture, a close-up picture of an ice core, which we've been introduced to before. And today we're going to delve into them a little bit deeper. A little background, when I've taught about climate change before, usually ice cores come up sort of as I don't know, briefly in a class. And they're really important to understanding past climates and our modern climate. It was just too easy to and too wrong to skip over them lightly. On the other hand, this is an introductory class. It's a lower division science GE. And I'm a little bit worried about this because it's complicated stuff. It's kind of requires a high level understanding, and yet it's so critical to climate change. I've decided to include it. So I hope I have pitched this properly, and if I haven't, I want to hear about it in the discussion forum. I want you guys, and I expect that you will have questions and have some trouble understanding this stuff. I want you to post your questions and help each other out understanding it on the forum. I will chime in the discussion forum from time to time, but I find that when I do, usually everyone shuts up. And so I like not to participate in the forum because that's for where students should be talking to each other. So please go there and post your questions throughout the course, but especially on this. Okay, so let's dive in. So what can you figure out from an ice core? Why are scientists spending so much money, time, and effort on going all over the world to where there is ice, like Antarctica, Greenland, and taking out these cores? Well, here's what you can get from an ice core. You can study the water in it. You can study the gases that are trapped in it. You can study the dust that is trapped in it. And so water, gases, and dust, well, what can you tell from them? That's what we're going to talk about today. So here's sort of skipping to the end. The water in an ice core can tell you the past global average temperature. How? I don't know. We don't know yet, but by the end of this lecture, we will. And from that data, they make these graphs. Now, this is 1, 2, 3 different graphs. The top on one is temperature, and it goes from now to 400. These are thousands of years ago, not 400 years ago. So that's a long time ago. The graphs match up, the axes match up, so you can compare them directly. This is temperature, this is carbon dioxide, and this is dust. And so we're going to study this graph more in the future. Right now, I just want to show you that they're showing the temperature going up and down for 400,000 years. How can you tell that from water? Well, let's see. To answer that question, we have to talk about isotopes again. We have already talked about isotopes, so see if you can answer this question. Remember, isotopes are blanks with different numbers of blanks in them. Think about that and see if you can fill them in. Okay, here's the answer. Isotopes are elements with different numbers of neutrons in them. Did you say elements for that? You should have. You might have said atoms. That's okay, but elements is better because an element is a specific thing. Atom is more general. So, for instance, carbon 14 and carbon 12 are two isotopes of carbon. Okay, the difference is this one has 2 extra neutrons. That's all. Okay. So previously we discussed an application of studying isotopes for dating stuff. All right, so we talked about the half-lives of isotopes, and we showed that if you have a radioisotope, over time it decays, and over a certain length of time, half of it will decay, and then over another equal length of time, another half will decay, and that's called the half-life. So those are radioisotopes, and they're useful in decaying stuffs, like this poor guy who died. Okay, so those are radioisotopes. So we will return to the use of radioisotopes and dating of ice cores soon, but for now we're going to remain focused on temperature. Remember, that was our question. I gave it away. How can you use isotopes to figure out global annual temperature? That is the question. Well, you could use a TARDIS to go back in time and use a thermometer, but unfortunately the TARDIS isn't real. So we need a different tool for doing it. And they actually have come up with a tool for doing it. Okay, here's how we're going to ease into this. The radioisotopes we've discussed so far are unstable. They decay over time. That's why we have that half-life. But there are also stable isotopes. For instance, oxygen has stable isotopes, and I've listed 3 of them here: O16, O17, and O18. These are isotopes that do not decay. They're not radioisotopes, they are stable isotopes, okay? So 2 different kinds of isotopes. So these were formed in the heart of stars, and they do not change here on Earth. Oh, Erath, Earth. We know their exact ratios on Earth. We know what they are. And I put this picture, this is from the Hubble, from NASA, the Hubble Space Telescope took this picture, and it's of a star that has begun to explode but then decided not to. So it's just about to go supernova, which is nuts that it does this sort of thing. But inside the hearts of stars, fusion reactions occur and new elements are created, larger ones from smaller ones, and they release a lot of energy when they do that. And that's where these different isotopes of oxygen were formed. Mostly we get O16, we have a little bit of O17, really a tiny amount, thousandths less of O17 and O18 than O16. But we know exactly what they are, and they are stable, so we can play with them. Okay, so although they don't decay, the ratio of these isotopes varies in compounds because they have slightly different chemical properties. And we're going to look at one example, that of oxygen in water. So water is a compound, and so some water molecules have O16 for the O part of H2O, and others have O17 or 18O, okay? So let's look at it. Oxygen and water. So remember, water, H2O, water is composed of oxygen and 2 hydrogens, and we're going to focus on the O, and it's isotope ratios. So here's the deal. The common lighter isotope of oxygen is O16. When it's in water, it evaporates. The water evaporates more easily than the rarer, heavier isotope O18. So a water molecule with H2O16 evaporates more readily than O18. So what? Well, it also condenses and falls out of the sky more easily. Okay, because it's lighter. When the global climate is relatively cool, there will be less of the heavier isotope in the snow that falls and gets locked up in ice. When the global climate is cold, when we're in a glacial period, there will be less of the heavier isotope in the snow that falls and gets locked up because it never came out of the ocean. The heavier stuff, it's too hard for it to evaporate. It's too cold, not enough energy to get it out. So when it's cold, less O18 in ice. When the climate is relatively warm, there will be more of the heavier isotope in it. Okay? When the climate is relatively warm, there will be more of the heavier isotope in water, in the water that comes out of the ocean, and more in the snow that falls and the ice caps. So when it's warm, you'll get more O18 in the snow, which later becomes ice. Okay? So what are we going to do about that? So what you can do is you just calculate the ratio of these isotopes to each other in a sample, and you have what's called a proxy of the Earth's temperature. And so I made one. Here's my graph. I made this graph. Here's your ratio of isotopes from small to large, a ratio being one number divided by the other. And so if the ratio, in this case, if your ratio is bigger, then the global temperature was warmer. If the ratio is smaller, then the global temperature was colder. That's what they do. Okay. So I just want to make sure you understand this term, the proxy. A proxy is a figure that can be used, a number that can be used to represent the value of something else in a calculation. Okay, so we're using the value of this to represent the actual temperature. Okay, so the ratio of isotopes that they can measure is going to be a proxy for the actual temperatures that existed. So, but I'm going to sort of do a little bit of review here. This is the reasoning behind the whole scientific effort to make cores in Antarctica. So water falls from the sky as snow in Antarctica. Okay, we'll think of that as a sample of the oxygen isotopes from that time, from when it fell. The ice, the snow, which is ice, gets buried, and it stays buried for thousands of years. The ice and the oxygen isotopes it bears remain unchanged that whole time because these are stable isotopes, not radioisotopes. And that's an assumption that must be looked at very carefully, that there's no change in this stuff over time. Does it melt and flow? Does weird things happen down there in the ice? I'm sure they've looked at that and studied that and decided that no, it is stable. Fourth, if we know how old a layer of ice is, and we'll talk about that soon, we can figure out what the ratio of isotopes was in the atmosphere when that ice was trapped. Okay, so we need to know how old it was. We need to know what the ratio was. So if we know the ratio, we at a certain time, we know what the global average temperature was in the year that ice formed. Okay, so that is the whole reasoning of using these ice cores to figure out past global temperatures. Now, I hope that this is true. If it sounds like a fragile tower made from cards, like first this, then this, then this, then this, and we can actually go there and collect it and measure it, then you would want to get independent corroboration. You don't want to just bet the whole house on one thing. We want another set of data, another way of doing the same thing. And if they say the same thing, then we're confident we're getting a picture of the truth. But if they say different things, then we have to go back and re-examine our assumptions and look at the science and improve. Okay. The thing is, we do have independent corroboration from this ice core thing. We have it in the study of fossilized carbonate shells. Now, I'm not going to go over that. You're welcome to look into that on your own if you want. But basically, shells of things that live in seabeds, like in marshes and seabeds, so clam shells and so forth, they are made of carbonate. And carbonate incorporates water. So, and then very frequently carbonates accumulate from all the shells that pile up, and those become rock. It becomes limestone, and it can be dated using radiometric dating, and the oxygen isotopes can also be sampled. So you can do the same sort of thing, but not in ice, instead in carbonates, and you find, I believe they found very close to parallel data. Okay, but I'm not going to go into that. I want you to stay focused in trying to understand what's going on with these ice cores. Okay, so let's return to this question. How do you know how old a particular layer of ice from a core is? How old is it? Well, there's different ways to do that. One is by annual layering, and in the background you can see this ice core has a bunch of layers on it. And apparently, I guess at different times of the year in Antarctica, the ice is different. Maybe it snows more in one part, or maybe it gets warmer in another part, and that changes the consistency of the ice. But that is good for only a little ways down into the ice. After a while, it gets kind of mushed together, and the layers aren't so clear. But you can go down a little ways using layer. The second thing is you can get markers in the ice from known events. So if, let's just say this is some volcanic ash, and we know that 10,352 years ago, there was a gigantic volcanic explosion that left a covering of ash over the entire Earth, then we know when we see it where we are in the time span. Excuse me. So huge volcanoes are known markers. There are other kinds of markers too, I think. And lastly, there is you can use radioisotope dating of the dust found in the ice core. So you melt the ice, a little bit of dust, you gather that, and then you sample the radioisotopes in that. And there's different radioisotopes that you can do. They're working on this. So actually, in my research on my literature research on this subject, I've discovered that this is complicated and difficult. There, for instance, the deeper the ice gets, the more it gets squished together, and so it flows a little bit, and so that makes it harder to interpret where you are in the core. Just for instance, it's one of the many problems, and there's a whole area of scientists who are focusing on this area, trying to get at the science and the technology for sampling these, get it better and better, and trying different ways and seeing if their data agree and so forth. So they're working on it. Okay, I wanted to get to the bubbles. So we've talked about the water, we've talked about the dust, and there's also bubbles, gas in there. Bubbles are important. Wow, that's quite a bubble. Anyway, why are they important? Well, if you melt the ice in a vacuum, you can gather the gas from the bubbles. I don't know how they do this, such tiny little amounts, and yet they're able to sample it out and figure out what's in it. Pretty amazing. This is a direct sample that the atmosphere, or the gas in a bubble, is a direct sample of an ancient atmosphere. It's just been sitting there all this time doing nothing, they think. That is super important. You will see why we're going to talk about the gases that they have found and how they've changed over time and how that relates to the temperatures of the globe at the time. And it's very, very important. But we're not going to do much of it now. Just want to show you in this graph we saw before, this middle one shows carbon dioxide. So carbon dioxide levels apparently in these little bubbles have gone up and down too. And we know when that was because we've got this graph of global average temperature based on the oxygen isotopes. And notice how parallel they are. Temperature goes up when carbon dioxide goes up. Okay, so we can look at the past and the relationship of temperature to carbon dioxide. Boy, that's really parallel. So that has implications, and we will discuss those as we go on. Okay? So, like anything interesting in science, many unanswered questions remain, and the science and techniques of ice core analysis are rapidly changing. The current view is not the last view, but it's the best view we have, and it's intriguing. Okay, so it's whatever you can do in science is what you know right now. And what we know right now is this is what we seem to be seeing. It doesn't mean that more experimentation in the future won't change this. In fact, it most certainly will. That's just what happens in science. But we're going to go with what we have and make the most of it. So here's a review, the bottom line. Unstable isotopes decay and are useful in radioisotope dating. Stable isotopes do not decay and are useful in determining global average temperatures. Ice cores contain ice and bubbles and dust, and these are all important. Ice is composed of water, from which ratios of oxygen isotopes are measured and used as a proxy for measuring ancient global average temperature. The bubbles contain samples of ancient atmospheres, which can be analyzed to determine levels of important gases. The dust can be used for radioisotopic dating and as time markers associated with past events like volcanic eruptions. And the techniques used to study ice cores are not perfect, but they are getting better rapidly, so stay tuned. And not to weaken this presentation, but never trust atoms. They make up everything. Get it? They make up everything. Hey, I had 7 seconds left before the 15-second mark, so I just want you to hear the ringtone today, and then we'll sign off. Here it comes. 1, 0.
I like to move it, move it. I like to move it, move it. I like to move it, move it. You like to move it, move it, move it.
Bye.